Hi guys. In today's video, we will see how a photoresistor works and how it is used. The photoresistor is a light-sensitive element. In practice, the photoresistor can be imagined with a resistance whose ohmic value varies in relation to the incident light. The physical phenomenon underlying the functioning of this component is called the photoconductive effect, and for each photoresistor it is defined within a certain spectral range. The resistive value of the photoresistor, depending on the light it receives, varies greatly from one type to another. The resistance of our component varies from a few tens of ohms, if it is exposed to very intense light, to a few tens of mega-ohms, over 40 mega-ohms, in complete darkness. With such wide variations in value, it is quite easy to make circuits sensitive to ambient light. The photoconductive effect is manifested by an electrical conductivity which increases with increasing light radiation, which invests the material. But let us now see the internal structure of this component. The photoresistors are made on an insulating support of ceramic material on which is deposited a semiconductor, which in our case is cadmium sulfide. The variations of conductivity are detected through two areas of highly conductive material above the semiconductor, consisting of a metallization, usually silver or gold with a double cone geometry, connected, and two terminals or reaphores. Its electrical symbol is like that of the resistor, enclosed in a circle with two incoming arrows. So, with a photoresistor, it is possible to make a kind of potentiometer which is not actuated by mechanical forces, but by light. So the most classic applications are those of brightness control, or backlighting on clock radio displays, in alarm devices, street lamps, or in general in all those automated lighting devices. So, let's now look at the simplified circuit diagram needed to test the operation of this component. So we have the usual Arduino UNO board and the small board, the HW486, which I bought with other sensor kits, which already integrates a resistor in series with the photoresistor. Then we have a 220 ohm resistor and a LED diode. So, the connections that we have on the photoresistor circuit are the connection to the power supply, which takes directly from the Arduino UNO board, the connection to ground, and the voltage output, which is formed by the resistive divider, consisting of resistor R1 and the photoresistor. So, just a few words about this board, the schematic, the connection diagram, and the one shown below. We have the 10k ohm resistor, which is this one here, and then we have the photoresistor in series, the two resistors in series. They form a resistive divider, which I'll go on to explain in a little more detail, and the value that we'll read through the analog input A0 is the voltage value that is presented at the ends of the resistor FR, the photoresistor. So, the value of the resistor R1, here indicated with R, is 10k ohms. Here indicated with 10.3. Instead, the photoresistor has a value which, as I indicated before, varies depending on the incident light. So with an intense light exposure, the value goes down to a few tens of ohms. Instead, in the absence of light or in complete darkness, the value can even reach over 40 mega-ohms. Let us now see, how as the value of the photoresistance varies, so does the voltage VO. To explain this, we must write the formula of VO as a function of the resistance R and the resistance FR. Therefore VO is equal to the value of VCC and therefore of the power supply, 5 volts, divided by the sum of the two resistances, that is the resistance R and the resistance FR, multiplied then by the resistance FR, which allows us to obtain the output value VO. I have repeated the calculation in the two conditions, i.e. FR equals 10 ohm, i.e. exposure to maximum light intensity, and FR equals 4 times 10 to the power of 7 ohms, which corresponds to this situation, in which the light received is absent, so we have total darkness. In the two cases, going to carry out the calculations, we have that VO, with an FR equals 10 ohms, therefore maximum exposure to light, is 5 mV instead of O with FR equals 40 mega ohms, therefore total darkness, we have about 5 volts. But we are interested in the intermediate zone. This zone here is that which presents the voltage variations ranging from 0.4 volts up to the zone before the curve of the graph, around 4 volts or in any case in the zones in this range. We can see how when the value of FR is equal to the value of the resistor R, the voltage we are going to read is exactly half of the supply voltage, so we find ourselves with 10 k ohms in this area, which corresponds to 2.5 volts. In the circuit we are going to see in a moment, we are going to match the exceeding of a certain voltage threshold VO with the switching on or off of a LED diode. Now let's take a look at the detailed diagram of all the connections. So I would like to say that it is not essential to have this board to test the operation of the photoresistor, and therefore it is not necessary to buy a whole kit, but it is enough to have the photoresistor and a 10 k ohm resistor. And that by buying the kit, as I did not have the corresponding wiring diagrams, which I have shown in this video, nor even some example sketches, so they did not waste much time, those who distributed that sensor kit. So let's go through all the connections, in this case to the board, so the ground, the 5-volt power supply and the voltage divider, at the ends of the photoresistor, which goes to the analog input A0. On the other side we have the ground connection, a 220 ohm resistor, which is connected to the cathode of the LED diode. Cathode is the one identified by the flat part, on the edge of the diode. Instead, the anode is connected to the digital output D2. As for programming and power supply, I always recommend using the USB port, which provides the 5 volts for operation and also allows us to program the Arduino UNO board. So let's see the sketch. To test the operation of the photoresistor, first we define an integer value type variable and initialize it to 0, then we define the sensor pin, which is the analog input pin A0, and we define the pin, output pin 2, which is the digital output pin. Let's now see the setup. On the setup we have the initialization of the serial, at 9600, and the definition of the output pin, as the output. Let's now see the loop. On the loop we have the storage in value of the value read from the output of the photoresistor circuit, which goes on the analog input. The stored value is then displayed is printed on the monitor, through the serial print. At this point, we pass in an if, where we have the condition of value greater than 650. I speak of the numerical value output from the ADC, which can vary from 0 to 1, 0.23. So in the case in which we have the value greater than 650, which corresponds to a low light intensity, therefore from 650 up to 1.023, which corresponds to total darkness, we have the switching on of the LED. On the other hand, if we have the value less than or equal to 650, the LED turns off. And at this point, we have the delay of 1 second and the loop starts again. Well, at this point, I'd say we're done, and if you liked it, remember to leave me a like and subscribe to my channel. But if you want to receive automatic alerts every time I upload a video, also click on the little bell. I'll say goodbye now and see you next time. Bye and have fun.